Good morning, sir.
Morning, Niranjan.
অর্গানিক ওয়ালপেপারটা কেমন লাগছে একটা
কি করে করবি সেগুলো? GIF না?
ব্যাকগ্রাউন্ড
Live নয়, live background.
ও আচ্ছা আচ্ছা, তুই কোথায় থাকবি?
আমি জানি না কেন তুমি ভাবো আমি
তাও কনাদ মনে হচ্ছে।
এই কোনাদ মনে হয়
আমি জানি না কেন তুমি আমাকে কলা গাছের মতো
এই কোনাদ মনে হয়
করো। আমি কি কলা গাছ, আমি কলা গাছ না, আমি কি কলা গাছ যে তুমি আমার কলা খাবে।
কি ভয়ঙ্কর গান!
ফেলে আরেকটা 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 কলা গাছ হবে। আমি
করে স্যার এলে বলবি না
কনাদ সাবধান, স্যার এলে কিন্তু বন্ধ করবি।
সময়ের সাথে সবাই
ভয় পেয়ে যাবে স্যার এসে।
আমার তাই
এই গানের লিঙ্কটা পাঠা
গাছপালা হয়ে থাকে হয়ে থাকে। আমি কি কলা গাছ, আমি কলা গাছ না, আমি কি কলা গাছ যে খেয়ে চোখ না ফেলে দেবে। আমাকে ছুঁড়ে ফেললে আমারই আমারই ওপরে পিছলা খাবে। চম্পা খেয়ে আমার কথা ভুলে যেও না, পাশেই ছিলাম আমি সাগর গলা, শিখর অনেক ভেতরে গিয়েছিল শুধু তোমার জন্যে সোজা ছিল আমার কেন তুমি ভাবো আমি কলা গাছ আমি জানি না কেন তুমি আমাকে কলা গাছের মতো ব্যবহার করো আমি কি কলা আমি কলা গাছ না আমি কি কলা গাছ যে তুমি আমার কলা খাবে
গানের সঙ্গে অত ভিডিওটা আরো ভালো লাগছে।
আরেকটা 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 কলা গাছ হবে
স্যার আসছেন।
Good afternoon.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon. Good afternoon. Okay, let's see how many of you are here. I guess everybody is here. Shubham,
Present, sir.
Moito,
Present, sir.
Ashif,
Present, sir.
Ditan, Sritoma,
Present, sir.
Nilanjan,
Present, sir.
Yabul,
Present, sir.
Girish,
Present, sir.
Shukorna,
Present, sir.
Shayanton,
Present, sir.
Devagro, Orko,
Present, sir.
Konath, Konath, okay, okay. Pritam,
Present, sir.
Medha,
Present, sir.
Arnav,
Present, sir.
Osri,
Present, sir.
Drishti,
Present, sir.
Suchishmita,
Present, sir.
Shruti,
Present, sir.
Anuraj,
Present, sir.
Pranav,
Present, sir.
Shomili,
Present, sir.
Shaureen,
Present, sir.
Akash,
Present, sir.
Mandash. What happened, Mandash? Yours, it doesn't work, Mike? Aditya,
Present, sir.
Anirban, Surajit,
Present, sir.
Pratoy.
Present, sir.
Okay. Has Devagho left?
No, sir.
No, sir.
Okay. Because somehow he doesn't do the classes. He does other classes. He attends the other classes. Okay. All right. So let's start where we ended in the last class. All right. Is it visible?
Yes, sir.
All right. So in the last class, we were talking about the hydrogen bonding interactions, and I was trying to emphasize the fact that hydrogen bonding plays important roles in directing the properties of bulk systems, and not only in the materials that we see around where such kind of interactions are possible, but as all of you know that hydrogen bonding is a very important interactions in biological systems. For example, the structure of proteins, which I will talk about a little bit, and also the properties of many molecules which are tuned by hydrogen bonding. So the geometry of hydrogen bonds and the strength of hydrogen bonds dependent on how two electronegative atoms are disposed with respect to each other. For example, here, as you can see, that this NH group is interacting with this oxygen, and this nitrogen and oxygen distance should be optimum, and absolutely this nitrogen, hydrogen, and oxygen angle should be such that it should form strong hydrogen bonding interactions. And it depends on the distance between the nitrogen and oxygen, as just I mentioned, but it should also depend on nitrogen, hydrogen, oxygen, this NH and O angle. And if it forms an hydrogen bonding interaction with a, let's say, an amide or an amine interacting with a carboxylic acid oxygen or a carbonyl oxygen like here, it also sometimes depends on the dihedral angle of the HA, that means acceptor. So here you see that theta, which is this one, is called donor. So NH group is the donor of the hydrogen bond, and oxygen is the acceptor of the hydrogen bond. So you call this one as D, this one as H, and DH and A angle with within the 180 degree. If it is linear, then it is the strongest hydrogen bonding possible. But even if it deviates a little bit from 180 degree, hydrogen bonding interactions still there, but hydrogen bonding interactions are getting weakened as you decrease the angle from 180 degree. So along with that, sometimes this angle phi, as you can see that, which is basically the hydrogen and the acceptor, and then you can have some group here, that angle phi is also important, and in that case it is ideally, if it is 120 degree, the hydrogen bond is stronger. Now electronegative groups which bring together, just like the example of HF that I told you is in the last class, it forms such a strong hydrogen bonding that it exists in solution as HF2 plus. So the proton in fact resides exactly the middle of the two fluorine atoms, and they form a linear 180-degree angle, makes it very strong hydrogen bonding interaction. And the distance, what about the distance? The distance is like if you have an oxygen OH, say for example, you may consider the hydrogen bonding in water, where the hydrogen comes between the two oxygen atoms, and from crystallographic study, where you get information about bond distance by X-ray diffraction of solid, you get information about these two heteroatoms, not the hydrogen, because hydrogen cannot be located by X-ray diffraction. Hydrogen requires a neutron refraction. So hydrogen cannot be located. Only thing is that in the electron density mapping, hydrogen is placed there, and this way you get an idea that where hydrogen is. But the distance that is considered for hydrogen bonding interaction is between the two oxygen atoms, and if it is within the distance of 1.6 to 1.8 angstrom, that's strongest hydrogen bond distance. And in case of nitrogen and oxygen, this can go up to 1.8 to 2 angstrom. So the longer the distance is, the weaker the hydrogen bonding is, and in some cases 150-degree to 160-degree angle also gives rise to a hydrogen bonding. And if that phi which I showed you sometime, even if it deviates to 130-degree also, hydrogen bonding still works. So considering that hydrogen bonding is a weak interaction, but it plays pivotal role in dictating the properties of bulk, and also it plays important role in biological system, as I just mentioned. The structure of protein, the secondary structure of protein, like hydrogen bonding interaction in between the amide linkage or complementary hydrogen bond, like the structure shown here. So this is a peptide unit, and it can interact with another peptide unit through complementary hydrogen bond. What is this complementary? The NH of one chain or peptide chain interacts with the carbonyl oxygen or amide oxygen of another chain, whereas vice versa, the NH of this chain interacts with the CO chain, and this way it gives like structure called beta sheet. And for alpha helical structure of the protein, it is within the chain where an nth unit, an n plus 4 unit, so NH of at position 1, and then n plus 4, which is 5th position hydrogen, a carbonyl will interact within the chain, and that gives rise to the twisting, and as a result alpha helix is formed, giving such kind of a helical structure of the protein. And you are all familiar with the hydrogen bonding, how it plays an important role. This is not in no way they are covalent bonding interaction. It's a hydrogen bonding interaction, again complementary. As you see, this is a hydrogen bond donor, oxygen is the acceptor. From one nucleobases to its other bases like AT and CG, they combine, and here 3 such hydrogen bonding interaction that makes the DNA structure double helical and unique in structure. So now again going back to water, because that is something, the manifestation of hydrogen bonding interaction in the properties is reflected, and it can form many different kind of structures when it is in the liquid, because of rapid dynamics of formation, hydrogen bond formation and hydrogen bond breaking continuously taking place. So you do not have any ordered structure. whereas in the solid you have an ordered structure, and this ordered structure in the solid ice gives rise to its unique properties. But it again depends on what environment your water or ice is. You can in fact restrict the motion of water molecule, and you can also impose a kind of a forced geometry of the orientation of water molecules in ice or water structure in some matrix. For example, I can have water in a lattice of another molecule. Will that the structure be the same, or it will be different? They again, that depends on what the host lattice allows it to adapt a specific conformation or geometry. As you see here, the different type of water clusters can form like this in dimeric form of water. One can see this in the lattice of another molecule. It can form trimer. Three hydrogen bonding interactions are taking place. It can form tetramer. 4 water molecules are involved in hydrogen bonding with each other. You have a pentameric structure, and this pentamer can have again different conformation. They can be a prism-like structure. You have a 3 molecules are on the top, you have 3 molecules at the bottom, and then you can have hydrogen bonding with each other. You can have a cage-like structure. That means it will form a kind of a cage, which you have a hollow space within, which is more like an ice-like structure. Or you can have a book-like structure, right? This is kind of 2 pages of the book. So 6 water molecules here. You see how all these have 6 water molecules, but they can give rise to different conformation depending upon where this structure is, structure is formed and within the cavity of which host. So host forces it to adapt sometimes different water molecules, because it may not allow its own structure of, and therefore water cluster vary from one to another. And there are several such water clusters have been detected that have unique structure formed by hydrogen bonding interactions, and they are trapped within the lattice of another host molecule or lattice of an host molecule, or in a matrix of some other solid. So this way we get information that water has a tendency to form hydrogen bonding interaction, giving rise to a diverse array of cluster formation. As you see here, that different type of water clusters are forming, and they are all dependent on the nature of the host molecule. Now here again, the structure of water cluster in solid lattice and liquid water structure. What would be the liquid water structure? So it is more like recently, a few years, I think about 6-7 years back, in 2014, the liquid water structure has been probed by ultra-fast X-ray of water below the homogeneous ice nucleation temperature. That is exactly where, before it adapts the water structure, the ice structure, how it in fact arranges itself before it adopts the ice-like icosahedral structure that is shown here. And there you see that 4 such water molecules, they occupy the corner in a like a square pyramidal kind of interesting geometry, like a tetrahedral type of geometry, you might assume this. And this has been probed by an ultra-fast X-ray probe, which is a technique that gives you a rapid X-ray, rapid X-ray irradiation of water, which is placed in a matrix. Again, it's a forced geometry, and from there you get a structure that how it is different from the ice structure. So this is nothing but that water is a simple molecule. We talked a lot about water molecules from our early school days, and we assume that we know water a lot, but actually still we do not know exactly how many different type of such interactions, hydrogen bonding interactions in water molecule can give, and what are their properties at in the bulk with different kind of structures of water. And this, as I said, that's a pretty complicated molecule, water. And this hydrogen bonding that gives you some unusual properties, which I already talked about: the floating of ice, its surface tension, its high heat capacity, and also how it freezes and gives rise to a different type of structures. So whatever we have covered so far that involves, other than in a molecular form, in a single molecule, you have ionic interaction, you have covalent interactions, and then when you go from molecule to beyond to another molecule, how two or more molecules in the bulk interact with each other. For that, we wanted to know the different type of weak interactions like dipole interactions, dipole induced dipole interaction, and then instantaneous dipole interactions, hydrogen bonding interactions. Similarly, there is a very weak interaction that also exists in molecule that contains aromatic ring. And this interaction is called the pi-pi stacking interaction. And this pi-pi stacking interaction is possible in aromatic rings, and there could be very different types of interactions, but most common interactions are that one is called edge to face interaction, which means that this hydrogen of aromatic ring, like the benzene ring, for example, if you have a hydrogen here, this hydrogen will occupy a position exactly just below the center of the aromatic ring. Similarly, this hydrogen on this will occupy a position just above the center of this ring. So this is called face to face pi stacking. And there is another kind of interactions which is called edge to face. That means the CH bond of one aromatic ring, if it is oriented just on top of another benzene ring in a perpendicular fashion, and then this CH and pi interactions also give rise to such kind of interaction. So these pi-pi stacking interactions, they also control the bulk property. For example, the slippery feeling of graphite that originates from this kind of structures, the face-to-face pi stacking interaction. Similarly, such type of interactions are also possible in other structures like the quaternary structure of proteins. Sometime, like that phenylalanine is one of the amino acid side chain, the R group of amino acid from a protein residue. So when one chain of alanine interacts with the alanine phenyl ring of alanine group from another protein chain, then they can form pi-pi stacking interaction and bringing different.
One, while staining of DNA, we use propydium iodide. So that molecule also binds to the DNA using this pi staining.
Correct. So, and the quaternary structure of Jyoti, the quaternary structure of proteins sometimes where one subunit of protein comes in close proximity to another subunit, and sometimes this kind of pi-pi stacking interaction, other than hydrogen bonding and dipolar interactions, these interactions also is responsible for bringing different subunits together to give you a quaternary structure of the proteins for many different big protein molecules. Like, for example, one important one is the globular protein hemoglobin, right? You have four such subunits, and four subunits comes together through these weak interactions. So as you see that other than this kind of interactions, you can have um, the other than hydrogen bonding interactions that we see here for two electronegative groups. Sometimes hydrogen bonding interactions takes place between a CH group and an electron deficient, an electronegative atom, and that's basically called as CH halide interaction, CHO interaction, CHN interaction, just to differentiate it with a true hydrogen bonding interaction. And also it's possible that an OH group can interact with a pi ring, electron deficient pi ring, or it can also possible that the pi ring may interact with an halide. So which is called and CHCl is a new thing which is called an halogen bonding, which is now recently a matter of discussion in solid state structure. So which is called halogen bonding, where a CH bond interacts with a halide ion. So in a solid or in a bulk properties of molecules, it is not that one interaction controls everything. A combination of several such weak interactions where they are possible. Okay, pi-pi interaction is not possible everywhere. If you do not have aromatic ring, there is no pi-pi interaction. If hydrogen bonding interaction is not possible because of the absence of necessary groups, then hydrogen bonding interaction is not there. Then dipole interaction or other interactions which are possible. If there is nothing, then you basically have a van der Waals interaction. And this van der Waals interaction is what? You are basically doing a kind of an asymmetry in the electron density of the atoms, and that created an instantaneous dipole which bring together system that are that comes close together. So from going from molecule to beyond, so you can think of not only that you have several molecules together and they are interacting with each other, and this way they give rise to something called supramolecular, that means beyond molecules, and this supramolecular structure of any system is dictated by these weak interactions or non-covalent interactions that we have just seen. And I think there is no point of talking about this effect of these weak interactions in the bulk phase properties. These chemical forces that we have learned, they dictate the melting point and boiling point, just like you have unique properties of water. Similarly, the melting point and boiling point will change depending on the strength of these intermolecular forces. The stronger they are, difficult to break it, and therefore obviously you need higher temperature to go against the lattice energy to break the lattice. Similarly, when there is a lot of symmetric molecules, they are also the symmetry that created a lattice, that also has an effect. And then highly symmetrical molecules sometimes have ability to rotate in the solid phase without disturbing the neighbor. Right? For example, you have all seen this thing at your home. You use this naphthalene ball, right? And this naphthalene ball, if you keep it for some time at home, eventually they vanish. So what they do, you never see any liquid formation from naphthalene. So going from a solid state, completely that this vaporizes and it goes to a completely in the gaseous phase. Because of the fact that naphthalene has two fused aromatic rings and it's highly symmetrical. Since it has a highly symmetry, although you have a pi-pi stacking interaction, each pi interaction in the lattice, but what happens? They have a much ability to rotate in the solid phase. So because of the thermal motion in the lattice, the molecule has always a lattice vibration. And the energy that they gain from this lattice vibration, this energy they utilize to rotate in the solid phase because that's a planar molecule, so it rotates like that. And because of this, what they will do, they will gain sufficient enough energy, thermal energy, by spinning sitting at one place, and then eventually they get this escape energy by this thermal spinning so that they go directly to the gas phase. But if you introduce one methyl group or one polar group in naphthalene, say for example hydroxynaphthalene, just put one hydroxy group there, one naphthol, two naphthol, or whatever you do it, they are solid. And you cannot have this possibility because other than this interaction, now you have an OH group. So this OH group will interact with the neighboring molecules either through OH pi interactions, pi-pi interactions, or even hydrogen bonding interactions. As a result, what will happen? The lattice, since the molecule is no longer symmetric, the lattice will be more stable because of these so many interactions, and it just by doing this rotation thing is not be possible. It cannot get sufficient thermal energy through this process of lattice vibration, and therefore the molecules there in the lattice solid form cannot go directly to the gas stage. Sometimes we talk about there is a misconception that if you have a covalent bond, that probably the molecule will be very strong bond, and the molecule will have a high melting point. But it's not like that. There here you have to really keep in mind of a true bonding in a molecule where the atoms combine together to form the bond and interact with each other in a molecule. But effectively, these melting points, boiling points, and other parameters, they are dependent on their lattice structure, how they are interacting, how many different kind of interactions are possible, and whether that kind of interactions will really make the lattice form stable, then they will have a high melting point. The simple thing is, for example, the difference between quartz and simple glass, right? Both are made of silica, SiO2. But the difference is that the glass has a relatively, or simple silica, has a relatively less organized lattice, whereas quartz has a very organized lattice, and that makes this much more stronger in terms of its stability and also its melting point. Now comes the question, solubility. And I think I talked about this in the last class, that even if you try hard to take salt and try to dissolve it in oil, you won't be able to do that. But many organic molecules or water doesn't mix with, say for example, oil, kerosene, or other non-polar solvent like hexane, pentane, butane, all these kind of solvents. When not butane, I mean pentane and hexane and this kind of hydrocarbons. They are also non-polar. So the question is, we always talk about this, that like dissolves like. Polar solvent will like to dissolve polar compounds, whereas non-polar solvents will dissolve non-polar compounds. So if we talk about that why a non-polar substrate is dissolved in a non-polar solvent, in both the cases you have these London dispersive forces, but the London dispersive force, or what you call it, an instantaneous dipole interaction or van der Waals interactions, it is there in both the liquid or one solid, one liquid. Now in both the cases, even if you have these interactions are very weak interactions, they are much smaller. So if you try to mix this, the enthalpy change of the mixing will be close to zero. The mixing of non-polar solvent, when two non-polar solvents mix together, it is primarily an entropy driven. But this entropy is also not very high, but it's enough to allow mixing of these two non-polar solvents. But if you take a non-polar solvent or a non-polar compound to a polar solvent or vice versa, so even if you assume there, although they are not really equal, the London dispersion forces more or less are comparable. But the dipole-dipole interaction in the polar molecule are much stronger than the London dispersion forces. So the energy that will be released from the polar-polar interaction, which will be much more negative compared to the non-polar-polar induced dipole interactions, right? Induced dipole. Therefore, more energy is released by having the polar molecules aggregate and the non-polar molecules aggregate separately. And therefore, they will make layers, and therefore, there will be no mixing. So this is the solubility properties of how these weak interactions, they also play important role in the different kind of properties of different molecules, either melting point, boiling point, their structure, their properties, and their solubility. Sometimes their lattice structure allows whether they can remain in solid form, or they can go directly to the liquid form, or bypassing the liquid form they can go to the gaseous form. All these properties are dictated by intermolecular forces. So in a nutshell, what we have talked about is the different type of interactions, the intermolecular forces that we talked about. We first ask this question whether there is any ions involved. If the answer is yes, there are polar molecules and ion both present there or not. If the answer is no, then it is purely ionic bonding. If there are polar molecules and ions both present, then you can have ion dipole interactions, like ion and the dipole of that molecule. If ions are not involved, then polar molecules, whether the molecule is polar or not. If the molecule is polar, we can check if there is any other interactions like hydrogen bonding interactions or not. If there is no hydrogen bonding interaction, there is a possibility that there could be a dipole-dipole interaction because the molecule is polar. So therefore, it can create a dipole, and then dipole-dipole forces can gives rise to its property. And if there is a hydrogen bonding interaction, hydrogen bonding will dictate their properties. And if there is none, then it is basically a London dispersion forces, which is basically nothing but an induced dipole, like the one I talked to you about, the liquefaction um, of helium or other non-polar gases. They can be formed to liquid just by this. And all these, in fact, in general, these van der Waals forces are there. So they together, along with the van der Waals forces, are operational in the bulk, and all these are important in understanding the properties and their physical and chemical properties. So if you just look at the energies associated with, yeah.
So there are also cation pi interactions.
Sorry?
So there are also cation pi interactions.
Cation pi interaction is possible, yes, yes, also. Right. So, yeah, as I said, thank you for pointing out this. So here you see that I talked about the pi-pi interactions. I talk about that you can have an electron-rich group and pi, and in that case, since it's electron-rich, for the interaction with the aromatic ring, the pi must be electron deficient. But if your electron, pi being electron rich, and if you have a cation which is itself is an electron deficient, then there is a possibility of cation pi interactions. Yes. So in that case, you understand, right? I mean that electron density of the aromatic ring must be higher. So it should be electron rich aromatic ring. So now if we just compare the energy of different interactions, like simple bonding interactions like ionic bonding, covalent bonding, or metal-metal bonding, they are of very high energy. Like for ionic bonding, it can have 400 to 4000 kilojoule per mole, like the lattice of sodium chloride. You have a cation-cation interaction, cation-anion interaction, cation-cation repulsion, cation-anion interaction, and then anion-anion repulsion, and eventually the dominant factor of the ionic bonding is the lattice energy, and which I will talk about in my next class. You have a covalent bonding. This covalent bonding is actually the sharing of the electron pair by the constituent atoms, and here you have the electron density, the electron and nucleus interaction, and nuclear-nuclear repulsion, and the balancing force eventually forming a stronger covalent bond, which is in the order of 150 to 1000 kilojoule per mole. There would be a metallic bonds where you have only metal, just like the metals in the solid state that we see, where you have a cations, the metal ions, and then there will be a delocalized electron, and therefore electron is not localized on any one, and then electron can go from one to another, and as a result it will create a cation, and the neighbor will be anion, and at a given time its corresponding neighbor will be again a cation and then anion. So this cation anion interactions will make it a metallic lattice, like the solid metals, for example iron or copper or such kind of metal ions. So they are strong forces and they are bonding forces. So these are actually talked about bonding. Whereas the non-covalent or non-bonding interactions, which are the intermolecular interactions that we have been learning for the last two lectures, last class and today, are these interactions that we talk about. Ion dipole interactions, where ion and then a charge and a dipolar species when interacts, like the dissolution of sodium chloride in water. So sodium ion will be hydrated and it forms this aquated species. And this is also a strong interaction although not as strong as the covalent or ionic interactions or even metallic interaction, but it's also strong because of this dipolar interaction. So this is in the order of about a few hundred kilojoule per mole. Hydrogen bonding compared to that is very low, but you see even such weak force like hydrogen bonding, how they can tune the properties of bulk where such kind of interactions are possible in molecules. You can have a dipole-dipole interaction. You have ion dipole interactions, ion and induced dipole, where you have a polarizable electron density around a molecule which is possibly can be polarized by the induced biweeks cation. And you can have dipole induced dipole, where the dipole of one can induce another dipole of other molecule, the neighboring molecule, and this way a whole bulk will be polarized. All the molecules in the bulk will be polarized, and that talks about that dipole-dipole, which is weak, and then you have a London dispersion forces where you have polarizable electron. There is no dipole, but you will have a polarizable electron density, and you just give an instantaneous, instantaneous force like pressure or something that can that can polarize one molecule, which in turn will induce this polarity to its neighboring one, and it's a very weak, as you can see, just between 10, 20, 30, 40 kilojoule per mole, depending on what are they, and this also is reflected in the bulk properties. So you have seen that these are simple things. You have encountered this thing in one place or other. You have seen in different molecules their properties, like hydration of sodium chloride, like dissolution of sodium chloride, the properties of water, the solid state structure of iodine or naphthalene, their properties. Dipole induced dipole can be created by putting one polar molecule in a non-polar molecule. Ion can induce dipole, like binding of oxygen to iron center, that eventually creates this kind of things in hemoglobin, which we shall talk about a little later, much sometime. And then the London dispersion forces, that how you can liquefy relatively less polar, or actually simple some gases which have no polarity, so that there is a dipole is not present at all, but you create an instantaneous dipole. During this whole discussion, one thing we talked about quite often is the electronegativity, right? Because you remember that when we talked about these weak forces prior to the discussion on of these weak non-covalent, non-bonding intermolecular forces, we talked about the considered the covalent radii of two different type of atoms, where the difference in the electronegativity can cause polarization. So all these things like the dipole-dipole interaction, dipole-induced dipole interactions, here what you are talking about is that some bond must be polarizable. Now this polarization is created because of the fact that you basically have a charge which is created on one of the constituent atoms, and or both of them, either in the positive charge or in the negative form. So delta plus or delta minus, just like here you see that you can polarize this H bond, and as a result, since you have an hydrogen involved there, it forms an hydrogen bonding interactions. If you have B here, then the B, if is a delta plus, then here an A, which is delta minus, can interact with another molecule. So electronegativity itself is and very important parameter that controls many properties. Now, what is that parameter and how it can be used to understand that how much polarization can take place on an atom in a molecule. Since electronegativity is a property of an atom in a molecule, so therefore the electronegativity is a power of an atom in a molecule, because electronegativity outside atom molecule of an atom outside molecule has no meaning. Electronegativity is a property of a molecular property when an atom is in a molecule. So it's a properties of an atom, but it is only reflected when that atom forms bond in a molecule, and then it is manifested through its attraction of electron density towards itself. Say for example, if I write down a simple molecule HCl, you can write it down that H plus or Cl minus, or you can write it H minus Cl plus, and you can write down all this resonance structure, or delta H plus on hydrogen, delta H minus on Cl, or delta minus on hydrogen and delta plus on chlorine. But you can write all the ionic resonances that are possible. But not all of them will contribute equally. Some resonance structure you all know from your organic chemistry concept, that not all these resonance structures contribute equally to the overall energy of the molecule. The ionic resonances, their contribution will not be the same to stabilize the molecule. So the question is, electronegativity is something that cannot be measured. It can be calculated. So here, if I write it down, you might say, okay, I prefer this one, H plus and Cl minus. Why do you say so? It is more like that it is easy to, from a concept of ionization energy, it comes to your mind that, oh, because hydrogen has a one electron and it is easily be ionized, and chlorine atom, which lacks one electron to to have its closed shell electronic configuration, and therefore because of its high electron affinity, I would like this one, not this one. So you see here that the constituent atoms, atomic properties like ionization energy and electron affinity is coming into picture. What is to do with that in electronegativity? As I will show you that how electronegativity is related to ionization energy and electron affinity. So we know that chlorine has much greater electron affinity, but fluorine is most electronegative when it forms molecule. The second question is that electronegativity of an atom will always remain same, or it depends on something else? I think I touched upon this in the last class, that electronegativity keeps on changing as certain amount of charge accumulates on that atom. Is it possible that you can have, we talked about fluorine in a molecule is more electronegative. Is it possible that you can have other species which is more electronegative than fluorine? If so, how? These are some intricate questions that we must look at, and for that, we must look at not the Pauline's electronegativity definition of its attraction power. Just give me a second. But it is the power of dragging the electron density of a bonding electron towards itself, but that's not the case. Then the one structures that we have drawn there, which was involving the electron ionization energy and electron affinity. Hello. Who are you? First year? Yeah, but I am in the class right now. Can you just call Saraswati Bhattacharya? Yeah, in the academic office. Do you know her? Do you know her number? The extension? Yeah, its extension number is 2236. Okay, you talk to her. She will be able to answer your question. I'm in the class right now. Okay, sure. All right. So the Mulliken's electronegativity, Mulliken came up with his way of understanding this. And Mulliken's electronegativity represent an average of the binding energy of an outer electron in an atom and its corresponding negative ion. What does it mean? It does mean that if I want to, if somebody is putting an electron, it is something like the other one is getting ionized and the negative ion, which is pulling the electron density, it is satisfying its electron affinity. So Mulliken introduces the idea that electronegativity represents an average property over a range of ionization instead of being solely a property of the neutral atom. So it is not that it is just a neutral atom's property of ionization energy electron affinity, but it says that it represents an average of the property over a range of ionization, and that could be many different terms. So overall, the energy of the atoms in various state of ionization that can be expressed. What he said that he extrapolated this of ionization potential to electronegativity. Because if you want to express the energy of an atom in various state of ionization, that can be expressed in terms of this equation. So if you have this series where it is dependent on the charge, or energy is dependent on the charge, like Q, so it can be alpha Q plus beta Q square plus gamma Q plus delta Q4. So you basically energies of the positive and negative ions relative to the neutral atoms are conveniently and accurately expressed for a given atom by a power series in terms of Q. This alpha, beta, gamma, delta, they represent what they are. And what they are, I'll come to that point, and this energy involves ionization energy of the atoms, electron affinity of the atom, then you can have an so-called the you can call it the promotional energy associated with it. And all these different energies of the atoms, they are incorporated in it in terms of charge on that atom. So total energy, that in any total energy in different oxidation state, as you can see, of any atom, that includes ionization energy, electron affinity, promotion energy, or even hybridization energies. So this is an atom in its different ionic state. Chlorine, 4 plus oxidation state, 3 plus oxidation state, 2 plus oxidation state, plus oxidation state, and 0 minus 1 oxidation state. You have fluorine, this card belongs to fluorine. Here, this one, the middle one. So fluorine here coming down, and then it is coming here until F minus. But everybody is passing through 0, right? Where it is F0, the atomic state. So the first ionization energy and electron affinity are nothing but their two ionization potentials and electron affinity energy that fits in the polynomial equation. Hello? Class here. So you can express now the higher terms if you ignore, you can express that E is equal to alpha q plus beta q square. Now if q is positive, that represents what? That represents means you are putting a positive charge of an atom. So that means it is equivalent to ionization energy. So if your q is plus 1, then it is alpha plus beta, right? And this is ionization energy. Whereas electron affinity is a negative charge when it accumulates on the atom. That's basically an electron affinity. So if a q is minus 1, then E minus 1, which is an electron affinity, which is expressed in terms of a negative sign, and this is now q is minus 1, so this will be minus alpha plus q is minus 1 square, so this will be beta. Now you express that alpha plus beta, and this is minus alpha plus beta. Now if you take this minus this, that gives you ionization energy plus electron affinity, that gives you 2 alpha. So this minus this equation. So alpha is an ionization energy plus electron affinity divided by 2. So Mulliken definition of electronegativity, which is nothing but, it talks about this alpha term, which is an average of ionization energy and electron affinity value when this is there in its neutral form. But electronegativity, you can express that this alpha, you can express it from here as well, right? So if you take a derivative of this equation, dE over dQ, that gives you alpha plus 2 beta cube. And Mulliken says that electronegativity is equal to the slope of the curve, the energy, so the total energy versus charge graph. And at any point, if you take the slope, that slope is indicate the electronegativity of that atom in that molecule when it accumulates that amount of charge at a point of that curvature of that curve. That is its electronegativity. So it is basically electronegativity is alpha, chi is equal to total electronegativity that is given by alpha plus 2 into beta into q. So now if you look at it, that in its neutral condition, fluorine, when it is 0, right? The charge is 0. Total energy versus charge. In an atomic case, this graph corresponds to chlorine and this energy graph corresponds to fluorine. Now if you take a slope, which one is more electronegative? Fluorine is more electronegative than chlorine. But is that the case at any other point? Is that the case for every point? You see, it's not. Because as the charge accumulates on fluorine, negative charge here, fractional negative charge. As the fractional negative charge accumulates on fluorine and also on the chlorine at the same, the slope is different. And sometimes the charge on chlorine, on some oxidation state, some charge on chlorine in a molecule, when it accumulates, then it will be more electronegative. So if you just write down that chi is equal to alpha plus 2 beta q, and you can write this 2 beta in terms of B, then the rate of change of energy with charge, you can express that in terms of this, where partial charge delta, you can replace it with formal charge q. Then you can also write it, A partial A plus B into delta, because now you don't have -1, -2, but you have a fractional charge, so better A plus B delta. And this A, which is an electronegativity, you have seen this alpha, is an average of ionization and electron affinity, and that is an inherent or neutral atom's electronegativity. However, the parameter B is called charge coefficient, and it measures the rate of change of electronegativity with charge. Because what is B? If you take a second derivative, then B is nothing but it's a first derivative of d chi over dq, and that is that how the electronegativity is changing with charge. So this B, which is called charge coefficient, is the electronegativity where it changes. So it has two components. One is neutral atoms electronegativity, which is inherent electronegativity, which is present for every atoms in a molecule. And on top of that, there is another one which is called charge coefficient. As it accumulates charge on it, or whatever charge it is, then its electronegativity also changes. And this is something, is a very, very important one, that electronegativity varies. And this electronegativity can vary by group electronegativity also. You are familiar with the fact that acetic acid is a weaker acid than trifluoroacetic acid, because the electronegativity of the group as a whole of CF3 group is much more, because 3-fluorine can which can accommodate more negative charge on it, and therefore the CF3 shows much higher electronegativity, and this is called group electronegativity. When as a group it can gives rise to an electronegativity value. You can utilize this equation also exactly how much charge you have on constituent atoms. So Sanderson estimated this using an equation. This is something called electronegativity equalization. That the electronegativity of the two constituent atoms A and B, when they form a compound, then the electronegativity keeps on changing as charge accumulates on these two atoms until the electronegativities of these two atoms become equalized. This is something called electronegativity equalization principle. So if you have an AB molecule, the electronegativity of A is expressed in terms of the inherent electronegativity and the charge capacity and the charge on it. And in a molecule, the electronegativity of A and electronegativity of B will be the same, because they must be equalized at some point of time when they are in the molecule. And what is happening here? So delta A, that will be accumulated on the charge which will accumulate on each of these constituent atoms. Either one will be positive, the other one will be negative. So delta A will be the equal for both of them. So you write that AA plus BA delta A, that will be equivalent to AB minus BB into delta A, where delta is the charge on partial charge that accumulates on the constituent atom. Now you can equate you can just write down the equation and find out charge that accumulates on it. So the delta, which is a partial charge that accumulates on an atom, will be nothing but it is the difference between the inherent electronegativity of the two atoms divided by sum of the charge capacity, or the B value that we have seen here, the charge coefficient value of that atom in the molecule, which is constant, which depends on, again, on different molecules, different atoms have different values, and you can get this. Their ratio will give you the charge which will accumulate on delta on these atoms. So if you just look at it, for HCl molecule, we know that hydrogen is much more electronegative in Mulliken scale. Hydrogen, the inherent electronegativity for hydrogen is 7.17, whereas chlorine, the inherent electronegativity is 12.15. Right? Chlorine is more electronegative in terms of the ionization and electron affinity average, the one you get from inherent electronegativity. Whereas the charge capacity of hydrogen and chlorine, they are fixed. The 12.84 and 11.55. These values you can get from any textbook, because just by working with several molecules and the electronegativity of different atoms in different molecules, they came up, the Mulliken came up with, the Sanderson came up with this equation. And that tells us that the charge on hydrogen atom on HCl is plus 0.2. So you have approximately a 20% charge electronegative deficiency that is caused by the chlorine. So chlorine pulls the electron density towards itself until 1/5 of a complete ionization form. That amount of charge accumulates on hydrogen. Until then, this electron pulling by the chlorine will continue. And then once the charge becomes 0.2, then both are happy that hydrogen at plus 0.2 charge and chlorine on minus 0.2 charge, they have of equal electronegativity now, and that is reflected from the electronegativity. Okay, so this is what I wanted to tell you, that simply just by energy practical classes without doing experiment has no meaning. And I think that I will talk about that when you will really do the experiment, and that will have visual effect, and that will help you in understanding the theoretical aspect of the laboratory experiments. Okay, I'll see you again tomorrow at 10:30. If you have any specific question for today, you may ask. Otherwise, we'll stop here.
Sir, I had a question.
Mm-hmm.
Yes, sir. My question is that, sir, when you were discussing the hydrogen bonding of water molecules, sir, you named one structure known as a book. Sir, what is the number of hydrogen bond water molecules present in a book?
Sorry, I cannot follow your question. Number of hydrogen bonds?
In the book structure, when you were discussing, sir, what is the number of molecules there? Like in a dimer, we know 2. In a trimer, we know it's 3. And in a
these are different type of clusters. So you see that when you have a solid, it's a repeated unit, right? So yes. You have you have a three-dimensional structure and keeps on growing in every direction. So there is no unique number in that true sense, isn't it?
Yes, yes.
Correct. So in a lattice, it's an infinite lattice. But when you are talking about that, the lattice, every lattice has its own constituent unit also. So that is something like you can have two water molecules, you can form a lattice, but that depends on what is the surrounding force that is keeping the two intact and not allowing two to go further. Or what is the environment that is forcing it to have a cluster with 3, 4, 5, 6 water molecules. But these are within a confined space, within a guest, right? I mean water is a guest there, and you need a host molecule to have to see these structures. But in a true ice structure, as I have shown you, this is there is no confinement question. It can keep on going. So it's basically keep on going by keep on adding water molecules in three-dimensional directions.
Yes, yes. Okay.
Okay, so it seems that you have no other question. I'll again see you at 10:30 tomorrow. Tomorrow, what time will start? Okay, solid state. All right. So tomorrow, I will try to make it from the classroom. If I cannot, I'll just let you know by 9 o'clock. Okay.
Okay, sir.
All right.
Thank you.
Thank you. Enjoy.
Thank you, sir.
Thank you, sir.